Welcome to the Explainer. You ever wonder how a video game can have thousands of unique characters running around, or how a banking app handles millions of different accounts? Well, a lot of the time, the answer is a really powerful idea called object-oriented programming, or OOP. And today, we're going to break down the 4 pillars that make it all work.
So, right at the heart of programming, there's this huge challenge, right? Our world is filled with complex things, but code, it's just text. So, how in the world do you translate a real object, like a car, with its color and its speed, or a person with a name and an age, into something a computer can actually work with? Tackling this question led to a totally game-changing way of thinking.
So here's the plan. We'll kick things off with the big idea of programming with objects. Then we're going to dive into the 4 pillars that really give OOP its superpowers: encapsulation, abstraction, inheritance, and polymorphism. And at the end, we'll tie it all together to see why this is so important for pretty much all the software you use. Okay, so what is object-oriented programming? Well, forget about just writing endless lines of commands. The big idea here is to structure your code in the same way you actually see the world, as a collection of individual objects where each one has its own properties and its own abilities. Basically, it's a way for us to create digital versions of real things. So instead of trying to keep track of a bunch of separate variables like employee name and employee salary, we can just create one single employee object. This object holds all of its own data, like its name and salary, and it also knows how to do things like, say, ask for promotion.
And this slide just nails the 2 core ideas. Over on the left, you've got the class. Think of this as the architectural blueprint. The employee class sets the template. Every single employee is going to have a name, a company, and an age. Then on the right, you have the object. That's the actual thing you build from the blueprint. Saldina here is a specific instance of an employee with her own unique data.
All right, so that leads us right into our first pillar, encapsulation. Now that we've bundled up all this data inside an object, a new problem pops up. How do we stop other parts of our program from just reaching in and messing things up, or maybe changing data in a way that just doesn't make sense? How do we build a data shield? Well, that is exactly what encapsulation is for. You can think of it like building a protective capsule around your object's data. It bundles the data and the only methods that are allowed to touch that data together, and it just locks the door to any direct, uncontrolled meddling from the outside. And this slide shows you exactly how it's done. First, you make the data private, which basically locks it in a vault. Then you create very specific public doors. We call them getters to read the data and setters to change it. And for step 3, you put a security guard at the door. That setter can have validation rules to check any new data before it's ever allowed in. So what you get is controlled, safe access. If some other piece of code tries to set an employee's age to something crazy like -5 or maybe to 15 when your company's minimum age is 18, our set age method, our security guard, can just say nope and reject the change. This guarantees our objects never end up in some bizarre invalid state. Next up, our second pillar, abstraction. And this one is all about hiding the messy details. As our programs get bigger, the internal workings can get incredibly complicated. Abstraction is the tool we use to manage all that by only showing the stuff that's absolutely necessary.
Think about it like this. Your smartphone is a perfect example. When you tap the camera icon to take a picture, you don't need to know a single thing about lens apertures or sensor data or image processing algorithms. All of that insane complexity is hidden from you behind a simple button. That is abstraction.
And we do the exact same thing in our code. Whoever is using our employee class, they don't need to know the 12 different rules and checks for figuring out if a promotion is allowed. Nope, they just need to know that there's one simple method they can call: ask for promotion. All that internal, complex logic is tucked away, making our object really simple and clean to use. Now for our third pillar, inheritance. This is where things start to get really, really efficient. The whole idea here is summed up by one of the most important principles in programming: don't repeat yourself. Inheritance lets us create a whole family of related classes where new ones can just inherit all the properties and behaviors from ones that already exist. So let's start with our foundation, our base parent class. It's a generic employee. It's got the basic stuff, name, company, age, and the common things an employee can do, like ask for a promotion. This is our starting point. Okay, but what if we need a more specific kind of employee, like a developer? Well, instead of starting all over again from scratch, we can just create a new developer class and tell the program that developer inherits from employee. This sets up a parent-child relationship. And this is where the magic happens. Instantly, automatically, the new developer class gets everything the employee class has: the name, the company, the ask for promotion method, all of it for free. And then we can add the stuff that's unique to a developer, like their favorite programming language or a special ability to fix bug. It's all about building on top of what you've already made. All right, our final pillar has a bit of a fancy name: polymorphism. But don't let it scare you. It's a Greek word that just means many forms, and that's literally what it's all about. It lets a single action, or a single method, behave differently depending on what object is using it. Let's go back to our employee example. The action work means something completely different for a developer than it does for, say, a teacher, right? For the developer, work means writing code. For the teacher, work means giving a lesson. The command is the same, but the result is totally unique. So how do we pull that off in our code? Well, when we call the work method on an object we made from our developer class, it does its own unique thing. It executes its own special version of that method, and it writes code. But when we call that exact same work method on a teacher object, it does something totally different. It starts teaching. And that is the core of polymorphism. One single method name, work, can trigger many different specific behaviors depending on the object you call it on. So how does the program know which one to run? The secret is usually a special keyword, like virtual. When we mark the original work method in our parent employee class as virtual, we're essentially telling the program, hey, I have a default way to work. But if you're dealing with a child class, like a developer or a teacher, that has its own special version of this method, please use that one instead. So let's recap. We've got the data shield of encapsulation, the complexity hiding of abstraction, the code reuse of inheritance, and the many forms of polymorphism. So what's the big payoff? Why do pretty much all modern programming languages use this model? It's really all about turning chaos into order. When we use these 4 principles together, our code becomes way more organized, it's reusable, and it's so much easier to maintain and update. Instead of having this tangled mess of wires, we get these clean, modular components that just fit together. And that's what lets us build those huge, powerful applications that can grow and change over time. And that brings us right back to where we started, that big question of how to represent our world in code. With these 4 pillars, you really have the tools to model almost anything. You can create the blueprints, shield the data, hide the complexity, and build entire families of objects. The possibilities are, well, pretty much endless. So the real question is, what would you build first? Thanks for watching.